Hello, this is Dr. Hanaa Assil, and this is part 3 of the review questions on Modular Unit 1 in the IGCSE Chemistry Edexcel modular system. So this is for Modular Unit 1. Again, this part includes these topics. So let's take a look at some of the questions. This question says, tantalum metal can be produced by heating tantalum chloride and hydrogen gas in a furnace. The other product of the reaction is hydrogen chloride. Complete the equation. So basically we need to balance. So how many chlorines before the arrow? 5. So actually I need 5 HCl, but then I find that the hydrogens will not balance like this. There is no 2 times something. We don't usually use fractions. So we need to multiply that all through by 2. That means now I have 10 hydrogens and 10 chlorines. So I will need 2 of the TaCl5, 5 of the H2, and 2 of the tantalum. All of this now is balanced. As tantalum chloride is heated, the mass of solid in the furnace decreases, leaving tantalum as the only solid product. State how the data in the table shows that the reaction is complete. Well, what are we doing? We're heating the TaCl5 with hydrogen. It is changing into tantalum, which is a solid, plus HCl gas. So the gas is coming out and the mass is decreasing as the reaction proceeds until at some point the mass remains constant. So after 5 hours, no more decrease in the mass, and that means the reaction is complete. Now use the data to show that the formula of tantalum chloride is TaCl5. So how much tantalum do we have? The tantalum is the final mass of the solid. That's the mass of the tantalum. And the difference between what we started with and the final mass would be the mass of chlorine. So the mass of chlorine is the difference between the first initial mass and the final mass. And the final mass is the mass of tantalum solid. So we use that, and please remember these are in kilograms and we never work with kilograms, we work with grams. So multiply by 1000, this is the mass of tantalum, the mass of chlorine, divide by the mass number of each one, the numbers that come out, divide by the smallest. This is a ratio of 1 to 5, and that is why the formula is TaCl5. Another method of extracting tantalum is by reacting it with reacting tantalum oxide with carbon. So in this reaction, explain why this is a redox reaction. Again, we said when the question says that, we have to mention that that is because it involves both oxidation and reduction, and you have to be specific where is the oxidation and where is the reduction. So the carbon gained oxygen, that is oxidation. The tantalum oxide lost oxygen, that is reduction. 2000 moles of tantalum oxide is heated with this amount of carbon. Show by calculation that the carbon is excess. Well, we'll count the number of moles, or we determine the number of moles of carbon. Number of moles is mass over molecular mass. So I have this number of moles of carbon. Now look at the equation. What is the relationship between the tantalum oxide and the carbon? The number of moles of carbon should be 5 times that of the tantalum. So number of moles of carbon that we need is 5 times the 2000. So actually we need only 10,000. What do we have? We have 41,000. That is more than needed, and that is why we say carbon is excess. Okay? Calculate the maximum mass in grams of tantalum that can be obtained. from 2000 moles of the tantalum oxide. Again, we look at the equation. We're looking for tantalum. If the Ta2O5 is 2000, what is the number of moles of tantalum? Well, from the equation, it should be twice. So that is the number of moles that would be formed. Now we need mass. Mass is number of moles times mR, and the mass that comes out is in grams. Use the periodic table to answer these questions. Give the name of the element with atomic number 16. So I look at the periodic table. I am looking for the element with the small number 16. Atomic number is the small number. If you don't remember, there is a key in the periodic table. So the atomic number in this periodic table is the one that is down. In any periodic table, the atomic number is the smaller number. So which one has an atomic number of 16? Well, that's sulfur. Give the name of the element with atomic mass of 9. Atomic mass, of course, is the larger number. So which one has its larger number 9 or mass number 9? That is beryllium. Give the name of the element in group 3, period 2. So we look again at the periodic table. Where is the group and where is the period? Of course, the group is the vertical column, so that's group 3. Now, where is the period? Remember, we count periods starting from helium, not from lithium. So helium is period 1. We're looking for something period 2, group 3, that is boron. Give the electron configuration of silicon. Silicon, if we look at silicon, silicon has how many electrons? 14. The small number is the atomic number. It's the number of protons, and it's also the number of electrons in the atom. So how do we distribute 14 electrons? The first shell takes 2. The second shell can take up to 8. And we're left with 4 electrons in the third energy level. Explain in terms of electron distribution why sodium is more reactive than lithium. Again, going down group 1, reactivity increases. Why? Because sodium has a larger radius than lithium, less attraction forces between the outer electron and the positive nucleus, or you could say more energy levels between the electron and the positive nucleus, so the electron is lost more easily as we go down the group. Again, I'm reminding you, metals are more reactive if they can lose electrons more easily. Name the 2 substances that cause iron to rust. Again, we said iron is silvery gray, shiny in color, but if it reacts with what? Both water and oxygen, then it becomes, and we said, what is the name of rust? It is hydrated iron 3 oxide. State a barrier method that prevents rusting. Which kind of method is a barrier method? We said either painting or oiling or covering with plastic. Any of these are called a barrier method because they prevent the iron from reacting with water and oxygen in the air. So what about sacrificial protection? Please remember, sacrificial protection is not a barrier method. It is a method in which a more reactive metal such as zinc or magnesium is trapped to the iron or put in contact with the iron, and it works because the more reactive metal is the one that loses electrons and becomes oxidized instead of the iron. Please don't say the more reactive metal is the one that rusts. Again, I'm reminding you, the word rusting applies only to iron. Other metals, we say they corrode, not rust. So when we have the iron in contact with a more reactive metal, it is the more reactive metal that loses electrons and becomes oxidized instead of the iron. The diagram shows separation of crude oil into fractions. Again, I'm going to remind you, you are required to know the order in which these fractions come out and the uses of each one. So, what is fraction A? Fraction A is the one on top, that is the refinery gases. Again, that means The ones on top are the ones with less number of carbons and lower boiling point. What is F? F is butamine. Remember, as we go down in the fractionating column, the fractions have higher boiling point, more number of carbons. They are more viscous, less flammable as we go down the fraction. Okay, one of the fractions is kerosene. What is the use of kerosene? You should remember the uses. Actually, you should remember the uses of all the fractions. Kerosene is used as a fuel for jets or for aircrafts. Describe how kerosene can be obtained from crude oil. How do we separate the fractions in crude oil? Again, remember, please, the first thing we do is crude oil is heated and vaporized. Then it goes into the fractionating column where it is cooled and condensed to give different fractions at different boiling points. And we said the one on top is the one that has lower boiling point, less carbons, more flammable, and so on. Catalytic cracking is a process used to break down fractions containing long-chain molecules. Give the name of the catalyst and the temperature used for catalytic cracking. Again, remember, cracking is the breakdown of long-chain hydrocarbons into shorter chains. What is the catalyst and what's the temperature? The catalyst is aluminum oxide. Remember, you can refer to this as alumina or aluminium oxide, and 600 to 700 degrees Celsius. Explain why catalytic cracking is useful. Again, why do we need to break down long chain hydrocarbons into shorter chains? Because shorter chains are more flammable, more in demand. Ethene that is produced will be used to make polymers and ethanol. The table shows the maximum mass of potassium nitrate and maximum mass of sodium nitrate that dissolves in 25 centimeter cubed of water at different temperatures. Remember, you are required to be familiar with solubility curves. So we have a graph paper and we're supposed to plot the points that we have. So we're plotting for potassium nitrate and for sodium nitrate, and we are told to label. Of course, here I made it blue and red, but in your actual exam, you don't use colors. All of this is in pencil, and you need to label each one is which. The graph shows the temperature at which the maximum mass dissolved is the same for each solute. Determine this temperature. Where is it that the maximum dissolved at a certain temperature is the same? So this at a temperature of 67 degrees Celsius, the mass dissolved for each of them is the same. Use your graph to calculate the solubility in grams per 100 grams of water of sodium nitrate at 30. So we're looking at sodium nitrate at 30. And from the table, we have 24 grams. But here already mentioned that this graph is based on what dissolves in 25 centimeter cubed of water. So this is the amount that dissolves in 25 centimeter cubed of water or 25 grams of water. How much would dissolve in 100? That's what we're required to get. So 24 grams dissolved in 25 grams of water, how much in 100? And you cross multiply. 25 centimeter cubed of a saturated solution of potassium nitrate is cooled from 50 degrees to 20 degrees. So we're talking first of all about potassium nitrate, and we're cooling from 50 to 20. Use your graph to determine the mass of potassium nitrate that crystallizes. So at 50 we had 21 grams dissolved, but by 20 we have only 8 dissolved. So the rest is what crystallizes out. So we have 13 grams of crystals, and this is what we base the idea of crystallization from. When we say heat to point of crystallization, so let's say we're heating to 50 and then cool to form crystals. So when we cool, what doesn't dissolve would come out as a crystal. Give two characteristics of a homologous series. Again, I'm going to remind you, homologous series are groups of organic compounds having same general formula, same functional group. And you are required to know the general formula and functional groups for alkanes and alkenes. So please remember that. Alkanes have single bonds, alkenes have double bonds. That's a functional group. General formula means how much or how many hydrogens with respect to the carbons. So alkanes, Cn, H2n plus 2. So the hydrogens are twice the carbon plus 2. For alkenes, the hydrogens are only twice the carbon, so it's CnH2n. So characteristics of a homologous series, the main characteristics are same functional group, same general formula, similar chemical properties. A scientist reacts lead nitrate with sodium bromide, and the equation tells me that when I react lead nitrate aqueous with sodium bromide aqueous, remember we said all nitrates are soluble. All sodium compounds are soluble. Now when we react them together, they give us lead bromide, and lead bromide is a precipitate. So describe how the scientists could obtain a pure dry sample of the lead bromide from the reaction mixture. We already added lead nitrate to sodium bromide and got a precipitate. What should we do next? Filter through filter paper and funnel, wash the residue with a few drops of distilled water, dry between filter papers. This is the precipitation method for obtaining a salt. The scientist reacts an excess of lead nitrate with 25 centimeter cubed of sodium bromide of this concentration. First of all, show that the amount of sodium bromide is 0.05 moles, so calculate the number of moles. How do we calculate number of moles of sodium bromide? The number of moles is concentration times volume. Again, I'm reminding you, the volume should be in decimeter cubed. So the 25 you need to divide by 1,000. This gives me the number of moles, and it is 0.05. Now show that the maximum mass of lead bromide that could be obtained is 9 grams. So what is the mass? I look at the equation, show the relationship between the number of moles. I find that number of moles of lead bromide should be half of the sodium bromide. So I divide the number of moles of the sodium bromide by 2. Now what is the mass? Mass is number of moles times MR. That comes out to about 9.2 grams, which is about 9 grams. In presence of UV light, hydrogen reacts with chlorine to form hydrogen chloride, and we are required to use the bond energies to calculate delta H. Again, let us take a look at the equation. This is actually the equation. So we have one HH bond, one Cl-Cl bond, and this gives two HCl bonds, and we said reactants minus products, so my delta H is minus 184. Draw a reaction profile. I want to remind you there is something called reaction profile and there is something called energy level diagram. The reaction profile should show activation energy. So activation energy for that reaction and delta H should be in the reaction profile. So reaction profile, if we look at the delta H, we said that the delta H is negative. That means we're talking about an exothermic reaction, and you have to know exothermic means products have lower energy than reactants. Products have lower energy than reactants because exo means the reactants lost heat or gave out heat, so the products have less heat. Now, where is the activation energy and where is delta H? Remember that the activation energy is from the reactants to the top. The delta H is from reactants to products. And when you draw these, whether you're drawing the reaction profile or the energy level diagram, you have to write out what are the reactants and what are the products. Don't write the word reactants, products. No, specify what are the reactants here, hydrogen plus chlorine. What are the products, 2HCl with the balancing. So this is what we call a reaction profile diagram. If you were asking for energy level, I would just go from reactants to products, no energy of activation. The diagram represents electronic configuration of an atom of sulfur. Which period contains sulfur? Again, how do we know the period and how do we know the group? We said the group is the number of electrons in outer shell. So if I were asking for which group, I count the number of electrons in outer shell, it's 6, so this is in group 6. But which period, I count the energy levels. How many energy levels? 3 energy levels, so it is in period 3. What is the charge on a sulfide ion? Well, I look at sulfur. How many electrons in sulfur? In the outer shell, it has 6 electrons in outer shell. So it needs how many more to have a full outer shell? It needs to take 2, but when it takes 2 electrons, which are negatively charged, it becomes an ion with 2 negative charges. Calculate the relative formula mass of zinc sulfide. How do we calculate MR? We need to write the formula first. Remember, zinc has a valency of 2. Sulfur also has a valency of 2. Remember, sulfide means sulfur. So zinc sulfide is ZnS. And we said when each of them has a valency of 2, they cancel each other, so you don't write 2 under any of them. So zinc sulfide is ZnS, and you add the mass numbers of each, that gives the MR. What is the name of the particle labeled W? What is W? We said in the nucleus, we have something positive. The ones that are positive are the protons. The one that doesn't have a charge, that is the neutron. What is the mass number of this atom? How do we calculate mass number? We add up all the particles in the nucleus. So you add up all the protons plus the neutrons. These are 9 in the nucleus. These are symbols for the 2 isotopes of lithium. In terms of subatomic particles, give one similarity and one difference between these 2 isotopes. Remember, if I have isotopes of the same element, they have the same what? They have the same number of protons, because both of them will have same atomic number. So same number, and he's saying in terms of subatomic particles. So don't say that the similarity is same atomic number. No, he wants protons, neutrons, electrons. So similarity, same number of protons. Differences is they would have different number of neutrons. That's why they have different mass numbers. And then we're told the samples of lithium contain this percent of this and this percent of that. Calculate the relative atomic mass of this sample of lithium. Remember, to get the overall relative atomic mass, it is abundance times mass number plus abundance times mass number over 100. Remember again, the mass number here is 6 or 7, not 3. So mass number times abundance, you add them for all the isotopes, divide by 100, and this gives the relative atomic mass of lithium. The diagram represents structure of magnesium. So magnesium is a metal. Complete the diagram by adding the labels. Again, a metal is made up of what? Regular rows of positive ions surrounded by a sea of delocalized electrons. That's what we have in a metal. Now explain why magnesium is malleable. Why is a metal malleable? We said layers of positive ions can slide over each other when heated or hammered. Magnesium burns in oxygen gas to form solid magnesium oxide. So we want to complete this equation. First of all, the state symbols. Oxygen, of course, is a gas. Magnesium oxide, we are already told, if we don't know, that it is a solid. And then you have to balance. So we have 2 oxygens before the arrow. That means I need 2 oxygens after the arrow. And that means 2 magnesium before the arrow. Give a reason why magnesium is oxidized here. What happened to the magnesium? Magnesium gains oxygen. That's why we say it is oxidized. Okay, a student uses this method to make a solution of magnesium chloride. Measure 25 centimeter cubes of acid into a beaker. Add magnesium powder. Keep adding magnesium powder until it is excess. Remove the excess magnesium powder by filtration. Give a reason why the student uses powder rather than ribbon. We said we use powdered because powders have larger surface area, so this gives a faster reaction. Give a reason why the student adds excess of magnesium in step 3. Why do we need excess magnesium? We said this is to make sure that all the acid reacts. Calculate the minimum mass of magnesium needed to react with this amount and this concentration of HCl. Again, we're given information about HCl. That means the first thing I need to do is get the number of moles. This is a solution. Number of moles is concentration times volume. Remember to divide the volume by 1,000. Now that gives number of moles of HCl. And then we're asked about what? Mass of magnesium. I look at the equation. What is the relationship between the moles of HCl and magnesium? Well, magnesium is half of the HCl, so that's the number of moles. Now we're asked about what? Mass. Mass of magnesium is number of moles times its MR. This gives 0.6 grams of magnesium. Sodium sulfate can be prepared by the reaction between sodium hydroxide and sodium hydrogen sulfate. Sodium hydrogen sulfate is acidic, so basically we're reacting sodium hydroxide with an acid. A student adds 25 centimeter cubed of sodium hydroxide into a conical flask and adds 2 drops of indicator. Name a piece of apparatus that should be used to add the 25 centimeter cube of sodium hydroxide. Remember, when we're doing titration, we put the solution into the flask using a pipette. Describe the method the student should use to find the accurate volume of sodium hydrogen sulfate needed to neutralize the sodium hydroxide solution. So basically, we're explaining how to do titration. So remember, we already added 25 centimeter cube of sodium hydroxide and we added 2 drops of indicator. What should we do next? Fill a burette with sodium hydrogen. Remember, this is a question with 5 marks and it's basically asking you to describe titration. Fill a burette with sodium hydrogen sulfate solution. That's the acid we're using. Note the initial reading in the burette. Add to the flask until the indicator changes color because it was not mentioned which indicator we're talking about. Note the final reading in the burette. Repeat to obtain concordant results. Add drop by drop near the end point and determine the average volume needed, of course, using the concordant results. The student repeats the titration without indicator, forms a solution of sodium sulfate. Now describe how the student can obtain pure dry crystals from the solution. So we already have the solution and we want crystals. So basically we're explaining crystallization. So how do we do crystallization? Heat the solution to point of crystallization. Cool to form crystals, Then we filter the crystals, and if we want pure and dry, we can say dry between filter papers. Crystals of hydrated sodium sulfate decompose when heated. And this is the equation for the decomposition. Of course, it's hydrated, so it breaks up into the anhydrous and water, and we need to get what is X. Again, here we have the mass of the empty test tube, the mass of the test tube plus the hydrated salt, and the mass of the test tube plus the salt that was left at the end, which is the anhydrous. So, from this information, I can get the masses. So, the mass of sodium sulfate originally that is not hydrated without the water is the final result minus the mass of the test tube. What about the mass of water? The mass of water is the difference between hydrated and anhydrous. So we get the mass of water. Use that to get X. Again, we put it in the form of getting empirical formula. Divide by the MRs which are given, the numbers that come out. Divide by the smallest. This comes in a ratio of 1 to 10, and that means that X is 10. And the salt has a formula of sodium sulfate, 10 water. Again, if we have this and we're required to get delta H, remember, the reactants alone, we have 4 CH bonds, 1 C double bond C, 2 OH bonds, that's in the reactants. In the products, we have 5 CH bonds, we have 1 C single bond C, we have 1 CO and 1 OH, and the delta H is the difference between reactants and products. Explain in terms of bonds broken and bonds made why this reaction is exothermic. We said if we have a reaction that's exothermic, what does that tell us? That means the energy needed to break the bonds in the reactants is less than the energy released when bonds are formed, so more energy is released, so it is exothermic. Draw an energy level diagram for the reaction between ethene and steam. Again, I'm going to remind you, the other time we were required to draw energy profile diagram, and we said in energy profile we show the activation energy. Here we're just required to draw energy level diagram, no activation energy. This is exothermic, so products have lower energy than reactants, so the delta H is from reactants to products, and please label which reactants do we have, which products do we have from the equation as it is, and the delta H, of course, is an arrow going down. And that's the end of this for now. So I hope this was useful, and good luck in your exams, and thank you for listening.